Lithium-ion batteries are a critical component for electrified systems, particularly in the transport sector. Battery management systems are the intelligent algorithms that ensure proper use of batteries. But what makes a pragmatic and functional battery model when e-mobility starts to dominate our societies? Universal equivalent circuit models are seen as a preferred choice. They can accommodate phenomena such as calendar aging and cycling, dependency on a state of charge, and temperature. Impedance in equivalent circuit models reflects several phases in the electrochemical process of the battery. At low frequency, diffusion or resistance to mass transfer dominates. In the medium range, charge transfer from electrode to electrolyte takes over. Finally, at high frequencies, the ohmic effect is the one prevailing. Based on our focus, the Warburg impedance or a Randel simplified circuit will be the right ones to use. So the Warburg impedance circuit applies when diffusion is important to consider. We will start with the Warburg impedance circuit model. For that purpose, I'm using RF Blockset as it is intended for analysis in the frequency domain. Please note that current source and Warburg impedance are both complex numbers and frequency dependent. The result of the simulation will be logged to MATLAB Workspace. The elementary Randel circuit is very similar but does not include Warburg impedance. With help of a MATLAB script, results of impedance are obtained for both approaches. We can conclude that for sufficiently high frequencies, Warburg and Randel circuit models will end up giving equivalent results. We will now introduce a common BMS task, active cell balancing. This function is critical to ensure that no cell becomes a hotspot and terminates the life of a complete module prematurely. To succeed, we will need a physical understanding of the system, a supervisory algorithm, and then requirements that need to be met. Now we will see how an equivalent circuit model is used for a key BMS task, active cell balancing. So parameterization of a cell with intentionally discrepant values. We are using Simscape electrical. Then even the initial charge of the cell differs. Then the capacitive unit. To redistribute energy across various cells. And then a state-based supervisory logic using state flow. So we have two states, balancing state and inactive state. And then the simulation is now running. Results show balanced cell voltages across the complete discharge cycle. At the beginning, the BMS algorithm needs to be active. Then towards the middle, the cells are in natural balance. And then in the final stages, so we need to activate the algorithm again. Do you focus on characterization of batteries with test data? Have you identified simulation as a way to accelerate BMS development? Would a physical model be the best contribution to your existing workflow? Please reach out to me or to your local Mathworks office to learn more. All chapters for the More Electric Tech series are found in YouTube. Thank you very much for